In this lecture, we will discuss about the thermodynamic database which deals with the delta G or delta Tm that we discussed earlier, right, using different experimental techniques, as well as how to identify the residues which are important to stabilize a protein. So, in the previous lecture, we discussed about protein stability. What is protein stability? It is a free energy difference between folded and unfolded states, right. So, what is the value of this free energy change?
5 to 20.
It is marginal, it is about 5 to 20 kilocalorie per mole. So, there are various experimental techniques, right, which can provide the data on the stability. For example, thermal denaturation or denaturation denaturation. There are several experimental techniques such as cyclotron dichroism, fluorescence spectroscopy, differential scanning calorimetry. So, we can use these experiments to obtain the data on protein stability. Then we discussed about the contribution of different interactions, for example, hydrophobic interaction, electrostatic interaction, hydrogen bonds, van der Waals interactions, disulfide bonds, right, in the folded structure of the protein, as well as entropy contribution to the unfolded state. Then we combine these two types of interactions and we get the net free energy change between the unfolded and folded state and compare this data with the experimental data. How to get the hydrophobic free energy?
From the delta sigma.
From these atomic solvation parameters as well as the solvent accessible surface area of atoms in the folded and unfolded states. Likewise, the electrostatic interactions you can obtain from ion pairs or you can see from this Coulomb's law. You can get the hydrogen bonds as well as the van der Waals interactions, right, based on this distance. So, now we find that the free energy difference is marginal and the protein is stable for their function, and if you look at the protein structures, whether we are able to identify the important residues, right, which are stabilizing the protein. So, there are various methods to identify these residues, right, and one of the methods which you can obtain from computational aspects is based on the interactions which influence the stability of a protein. If you look into these protein structures, right, earlier we discussed the hydrophobicity is one of the factors, right, which stabilize protein structures. Hence, we use various interactions and various features based on the hydrophobic character. Likewise, how can we quantify the hydrophobic behavior of residues in a protein and long range interactions. This will tell you the information on how far two residues in a protein are interacting with each other, right, whether they make the long range interactions or the short range contacts and how many contacts one residue can make. So, we discussed about some features using long range interactions, for example, long range order or multiple contact index and conservation. So, conservation can be obtained from the sequences, right. You can, if you have the amino acid sequence, then you can obtain the homologous sequences. From the homologous sequences, you can see any position is accommodated by the specific residue. If there are various features, the main features we consider are the hydrophobic character of residues and long range interactions as well as the conservation. If you look into these three features, these hydrophobic character and long range interactions you can obtain from protein 3D structures, right, this is obtained from 3D structures. So, for the conservation you can get from amino acid sequence information. We can now explain how to get these features and based on these features how we obtain the data, right, which can stabilize a particular protein. So, step 1, we need to compute the values of these parameters for all the residues in a protein. For example, a protein contains 100 residues, for each residue we can calculate the parameters based on these specific characters like hydrophobic character, long range interactions as well as the conservation score. So, in the hydrophobic character we already discussed about the surrounding hydrophobicity. We can use this surrounding hydrophobicity to quantify the hydrophobic behavior of each residue in protein environment. Likewise, we can calculate long range order based on the contacts between two residues which are close in space and they are distant in the sequence. We use this information to calculate the long range order. Stabilization center is also similar to long range order. This also involves long range interactions. We can see some cluster of residues and these residues are having a contact among these two groups. Like the conservation score, it depends upon the location of residues which are occupied the same position, right, in different homologous sequences. Already I have discussed the development of these parameters, just I will outline again, right, how to get these parameters and how we identify the residues which are stabilizing in protein structures. The surrounding hydrophobicity can tell you the hydrophobic behavior of each residue in protein environment. How to get this surrounding hydrophobicity? Well, for each residue you can construct a sphere of radius r. Here you can see the radius is 8 angstrom, and identify the residues which are occurring within this limit of 8 angstrom, and we have the experimental value for each residues which is surrounded by a central residue. Okay, this is a central residue. Then we add the values and finally you get the surrounding hydrophobicity of the central residue. Like for example, if Hj, if j is T, we can obtain 3 1 in here. Okay, we can obtain the values with summation of Nij, right, which are the residues, right, of type I which are surrounded by residue j. For example, how many alanines or valines, right, surrounded by this 3 1n, multiplied by the hydrophobic index of that ith residue. For example, 5 i's, 5, then you can multiply with the value for the solution 5 times with these hydrophobicity values. So, here Hj is the central residue and Nij is the number of residues of type I around j, and Hi is the experimental values, either you can take from the octanol water experiments or the ethanol water experiments, right. So, you can use the values. So, finally, this will tell you the hydrophobic behavior in protein environment. So, in this case if you take a protein, the values for same residues at different positions are different. So, we can use this PDB param, right, to obtain the surrounding hydrophobicity. Just you go to PDB param I discussed in the earlier classes, and you give your input protein name, which protein you want to identify the hydrophobicity of residues. So, here the PDB ID is for MBN, it is myoglobin, and you have to click on surrounding hydrophobicity. Once you do this, right, you will get the values. For all the residues in a protein, you can see the surrounding hydrophobicity of each residues. For example, what is the hydrophobicity of tyrosine 103? 19.64, right. So, if you look into these surrounding hydrophobicity values, some residues are high in surrounding hydrophobicity and some of them are less. Can you find some of the residues which are very high in surrounding hydrophobicity? For example, if you put a range of 20 kcal per mole, leucine, this is more, and you can see isoleucine and alanine. Okay. So, these residues, right, 104, 107, 1010, okay, these residues they are high in hydrophobicity. So, these values will tell you which residues are having more contacts and which residues are enriched in surrounding hydrophobicity, right, in protein environment. So, now we have one parameter, the surrounding hydrophobicity, you can calculate from any 3D structures. Then the second feature, we can use long range order, right. What is long range order?
Number of contacts greater than.
So, you can see the contacts which are close in space, far away in the sequence. So, here are two parameters we need to fix, one is the in space. So, here we use the distance of 8 angstrom and the distance in the sequence. So, here also we can vary different distances, and here we use the cutoff of 12 residues. You can identify the residues and see which residues pairs are far apart at least 12 residues. So, for example, if you see this graph, right, I showed this earlier, if you take the 3 and 152 and if you take that I, if this is I, if this is equal to j, then you can say j equal to 98, for example, if you take this one 153, in this case I minus j, this is equal to 1, so Nij equal to 0, because we need I minus j equal to at least 12. So, if j equal to 98, if this is the j, then you can see I minus j, this is equal to 154, right, in this case this is equal to 52 plus 54, this is greater than 12, in this case Nij equal to 1. So, for each residue you can say how many residues which are far apart, at least 12 residues. If we take 152, how many residues which are forming the long range contacts? 98, 95 and this is 94. In this case you can see Nij, this is equal to 1, 2, 3, right, you can find it. Then if you have the Nij, we know the number of residues in a protein and you can calculate this long range order using this equation. right. If equal to 3, then 3 by for example 153, then you can get the values. So, you can use the PDB param to obtain the values. So, here if you give the same PDB ID and you give the long range order and if you submit, so you will get the numbers. If you see the numbers, many cases it is 0. Why this is 0?
Only local interaction.
Only local interactions, mainly because for MBN is a myoglobin, it is all alpha proteins, it contains mainly alpha helices. This is the reason why this value is 0. Some cases you can see higher number 0.026 or 0.013. So, if you look at different structures, if you take different proteins and you can see the variation of these numbers based on the number of contacts, right. If it, for example, if you take all beta proteins, these proteins you can see several residues are influenced with long range contacts and you see the higher values, right, in the case of these alpha all beta proteins. So, we discussed about the surrounding hydrophobicity and we discussed about long range order, and stabilization center is another property. These also mainly from the information regarding long range interactions. So, here if you see the two residues are the part of stabilization centers, right. If they are involved in long range interactions, they find this some cluster of residues which can form these contacts and then see whether these clusters are close to each other at least with the 10 residues. So, in this case you can use this server SCIDE. So, to identify the stabilization centers, it asks the PDB code, right, or you can upload your PDB file. Then the asking for this stabilization center, right, you can see from particular chain, or if you have more chains you can also see from the different types of chains. So, here this is the result. So, we can get the text as well as for the graphical, and here we see the chain information and the residue 17 is involved in stabilization center because this and this 27 they are having several residues in the center and they are interacting with each other. Likewise, for each pairs they have see they are forming the stabilization centers. Now, the fourth property that we use conservation score, right, because conservation score is also important for the stability because it maintains the same position from different homologous sequences, right. Already we discussed about the calculation of conservation score, right. What is the main information if we did require for calculating the conservation score?
Multiple sequence alignment.
Multiple sequence alignment, right. So, for example, if you have one sequence, you get the homologous sequences and do the multiple sequence alignment, and from that you can see which residues are highly conserved, right. For example, here if you see this one, right, you can see this highly conserved, all the sequences, right, it is mainly with leucine or valine, right. We discussed about the various methods how to calculate the conservation score, right. The simplest one you can see the U of I because unweighted frequency. In this case you can calculate by NA of I by N of I, this is the number of positions, right, how many amino acids of type I which are present in any particular position. This NA is amino acid, I is particular position. So, for each case you can see the conservation at any particular position I, you can see FA of I in the logarithmic of FA of I, or this A equal to 1 to 20 amino acid residues for any particular positions. I varies from 1 to the n, what is number, n is the number of residues in the protein, right. Fine. Then I show this picture, right. So, some residues are highly conserved, right, many the residues which are shown in magenta color, right, this one this highly conserved, and the one which is in blue these are variable. So, you can get these numbers between 0 to 9. In this case 9 is highly conserved and 0 is highly flexible, that is variable ones, fine. So, now we can calculate all the parameters, try take any structure, we can see the residue, this is obtained from the PDB, these XYZ coordinates, here you have the sequence here. So, for each residue you can calculate the conservation score and surrounding hydrophobicity, right, long range order and the stabilization center. So, this is called we can say surrounding hydrophobicity. So, now here we give the position, right, different types of amino acid residues. So, here this is the conservation score and here we have the hydrophobicity values we obtain from the PDB param, and LRO this also you can obtain from the PDB param, and finally stabilization center, that also you can see this is 1 or 0. If it is involved in the stabilization center, that is 1, if it is not involved in the stabilization center, then it is 0. So, we have the values. Now, the issue is we need to identify the residues which are involved in stabilization in the stability. So, we can try with the different cutoff values, right. With these cutoff values, when you identify the residues, that should match with the experimental data. In that case you can change your threshold, right. If you take a particular threshold, for example, surrounding hydrophobicity is more than 20 and LRO is more than 0.02, stabilization center equal to more than or equal to 1 and conservation score is more than or equal to 6. That means that residue should be highly conserved among the homologous sequences and it should have more number of contacts and they are also highly hydrophobic nature. It may lose some specific residues, for example, the charge residues, right. Also some charge residues are also having this type of more number of threshold values. I will show in the data. If you do these conditions, then if you see these numbers, which are the residues which satisfy all the conditions, conservation should be more than 6. In this case almost all the residues they are having more than 6, and if you see the stabilization center, that is more than or equal to 1, so everything is fine. So then you look for the hydrophobicity. What is the range we put? More than 20, right. If it is more than 20, then this will satisfy the condition. The long range order
0.02.
more than 0.02. So you can see these two values, but only this one will satisfy all the conditions. Then you can say alanine 110, okay, this is an important residue for the stability of the particular protein. You can see that this is the kind of residues which are stabilizing this protein structure. So now we want to compare whether you identify the residues which are comparable to the experiments or not, right. So we take a set of proteins, for example, we discussed about the T-barrel proteins. These proteins they have diverse sequence identity, but they are having common fold. If you see they are having some common fold. If you see these the alpha helices, right, and you can see inner part that is mainly beta strand, and if you look at the sequence they are alternate with each other, one is helix, one is strand, helix strand and so on. Then we check the data whether you can find any residues which are identified stabilizing or experimentally identified. So another case is glycine 229, this is here. So this residue is identified as stabilizing residues because they did the cytochrome mutation experiments, and if you do that, if they destabilize the protein, then you can say these residues are important for stability. So here the red ones we identified, these are all the residues which are mainly involved in stability. So glycine 229 you identified is involved in the stabilizing residues. Then after some time, after 2004 they identified that 16126, this also play important role in stability. So here you can see 16126, that is also here, right, and this residue is also identified as the stabilizing residues in this particular protein. Likewise you can see the several residues compared with the experiments, you can see these residues are important for stability, right. Another factor to see whether a residue is important for stability is the B-factor. So in this case if it is rigid, then if the residues are highly stable. So we calculated the normalized B score I discussed earlier, right. This is equal to B minus B mean, this is the average of these B factors, and B sigma is a deviation. So when you normalize, if it is equal to more than or equal to 1, this is flexible, and less than or equal to 1, this is rigid. In this figure, I showed this figure earlier, see several residues are in blue, okay, they have the low values, right, and some of them are red and yellow, right, they have the more motions, right, depending upon the B factors, right. So here you give the numbers, so some of them very high, they are flexible, and here in this case they are rigid. Fine. So now I identified some residues, I shows the data for some of the proteins. So these are the PDB code, right, 4-letter code, and see the stabilizing residues. So for example, glycine 139, valine 185, right, leucine, isoleucine, so on, several residues. So they are the 4 parameters for surrounding hydrophobicity, long range order, stabilization center, and the conservation score. So from all these numbers you can identify these, for example, these are all very high, it met all the conditions. And if you see the B factors, and most of them, for example, if you 91 out of 957, right, 931 out of 957, this is 97%. Here you see the B factors, they are negative, indicating that they are having one among the residues which are having the lowest atomic displacement in the corresponding proteins. We can calculate the average B factor. So here you can see they are having the B factors negative, so they are important for the stability, and most of the residues, for example 97% of the residues which are having the negative values So, then can see that okay, these are also probably a stabilizing residues in protein structures. So, now you want to see among these stabilizing residues are there any particular preference of residues, right, to be in the involved in the stability, right, as was expected, because we use surrounding hydrophobicity is one of the factors. Most of the hydrophobic residues they are important for the stability, because if you mutate these residues with the charge ones, right, this will destabilize the protein, that is fine. So, we got the information. If this is the frequency of occurrence of residues in the stability. So, value in isolation is very high, it is more than 10 relatively with other residues. And here you can also see that some of the charged residues they are also involved in the stabilizing residues. For example, if you see this arginine, glutamic acid, so here also you can see the preference, right, but the less compared to the hydrophobic residues. This will tell you not only the hydrophobic residues, but also the charged and polar residues are also involved, right, to stabilize these particular proteins. Then we group the residues like a hydrophobic and the sulfur containing and the aromatic, polar and charged. Here also you can see the preference of these residues, right, to be involved in the stabilizing residues. Then we see whether these residues are present in any secondary structure preference. So, mostly we can see the beta sheets and followed by these alpha helices and other residues. This to be expected, because the beta strand residues which are highly interacting with the other residues, this is the reason why many residues are identified in beta strands. If you see this figure, you can see that the stabilizing residues are mainly in the beta strands, but there are several cases in the alpha helices too. Now, if you look into these different types of stabilizing residues, and the question is okay, there are several residues in different beta sheets, whether these contacts or these interactions are forming a network, or they try to have a network of interactions. Likewise, if you see some students they go together, they will form some network of students together, always they go together. So, we checked that and interestingly found that some many cases S1, S2, S3 denotes the number of strands. This is strand 1, strand 2 up to strand 8. So, the residues we mentioned are the stabilizing residues. Mainly if you see in strand 7 we have 6 stabilizing residues compared with strand 8 and strand 5, right, strand 5 has 5, 4 and 8 has 2. So, but these residues they are interacting with each other, they form like a network of interactions. Mainly if you see this S5 to S8 you can see several residues which are interacting together, right, form a network of interactions. This also help to stabilize the protein and maintain the stability of several particular proteins. So, how to get this information? So, in this case we develop a server that is called the SRIDE, right, that is stabilizing residues in protein structures, right. It takes a PDB code, or you can upload your structures if you obtain the data from the MD simulations, right. Then we can specify the chain. If you want to get these stabilizing residues from a particular chain, you can specify the chain, or you can you put star if they take the first chain or all the chains. Then threshold values, this is not fixed, because we give the option to select the threshold values, right. You can use the E value mainly for the alignment and the conservation score, long range order or hydrophobicity or stabilizing center. So, you can give these values and then you can get the residues which are identified as stabilizing residues in any protein structures. When they developed this program, they started with the timbaral proteins because they are having specific character, then extended to the different types of proteins. Now, you can use for any proteins, you can give these threshold values and give your PDB ID, then you can get the stabilizing residues for any particular protein. So, we obtain the stabilizing residues, and one way we compared with the B factors, then we can also compare the stabilizing residues if experimental data are known. If several experimental delta G or delta Tm values are known upon mutation, right, then you can collect all the destabilizing mutants. Okay. In this case, if you mutate a residue, that will destabilize the protein, and see the mutants which are having significant deviation. For example, if you take 1 kcal per mole or 2 kcal per mole, and see whether these residues are also identified as stabilizing residues using these procedures. In this case, it requires the experimental data, right. It is good to have a unique resource, right, to collect this data and the form of a database, and if you have a database, you can query the database and you can get these residues which are destabilizing upon any particular mutations, and this can also you can verify whether these residues are destabilizing the protein So, that this is very important for stabilizing a particular protein.